This is a LattePanda Mu, a tiny but powerful single-board computer, and in this video, I'll show you how I turned it into the heart of this custom Cyberdeck. So what the heck is this thing, and why am I building around it? The LattePanda Mu is a single-board computer, or SBC, kind of like the Raspberry Pi. Both contain all of the necessary parts needed to run an operating system and various applications on a single board. But there are some very important differences. First of all, the Mu is a lot more powerful. There are now multiple versions, but even the base model has an Intel N100 4-core CPU capable of 3.4 GHz. All models also have 64 GB of onboard flash memory, which can be used to install an operating system if you don't want to put it on an external drive. Additionally, these have an x86 CPU architecture rather than ARM, and that means you can run more types of operating systems. Probably the biggest difference, though, is that the Raspberry Pi is a fully integrated system on a single circuit board, with I/O ports like USB, micro HDMI, and Ethernet, whereas the Mu requires a carrier board to break out these pins that you can see along its edge. Now, if this layout looks kind of familiar, that's because it's made to fit inside of a laptop-style RAM slot. Well, not actually inside of a laptop, but it uses the same connector. But wait a minute, I hear you say. Isn't needing another circuit board a bad thing? Well, yes and no. The thing is, with a custom carrier board, you get way more options. And fortunately, all of the information needed to design one is open source, so that's what I'll be doing in this video. But first, let's take a look at the basic carrier board that the manufacturer, DF Robot, offers. This will be the starting point for my design. This board functions similarly to a motherboard in a traditional PC. It provides all the mounting sockets and their electrical connections, and ties everything together. It also has all of the various I/O ports that you would expect. Power is provided via this barrel jack, with an operating range of about 10 to 20 volts. But, as I mentioned earlier, we're not going to be using this. But before that, I gotta figure out what it is that I'm actually building. This isn't my first foray into building something like this. Back in fall of 2023, I built this, my framework Cyberdeck. Check out that video if you haven't already seen it. I still really like this thing and actually use it a lot more than you would expect. But it's not without its flaws. No touchscreen, a non-mechanical keyboard, and the mini trackball isn't really ideal. Also, the ultra-wide display can be a little bit awkward for certain things, like browsing the internet. This time around, I would like to do something a little bit different. I'd like to do an even smaller form factor and add a touchscreen, and also have a slide-out mechanical keyboard. I came up with this basic concept. It's a tablet-style device, but with a keyboard mounted underneath that can pop out if you want to do some typing. Whenever I'm working on a project like this, it requires a ton of research on the internet, and you know what that means. Millions and millions of tabs open, which can be overwhelming. Well, not anymore, thanks to the new Opera One R2 web browser. In Opera, your tabs can be grouped into islands, helping you keep things organized. You can sort your tabs by topic into groups and expand or collapse them as needed to keep everything in order. Here, I've put several datasheets into one island to save space. Recently visited tabs also have traces, which helps you keep track of what you were working on. The darker the underscore, the more recently that tab has been opened. You can see that this was the last tab that I opened, then this one, and so on. You can even have two tabs side by side in the same window like this. I often found myself having to constantly switch between, say, a product datasheet and a circuit schematic. Now I can compare them side by side. No need for multiple browser windows. Listening to music while working helps me stay focused, and Opera's floating music player lets you control your tunes without having to stop what you're doing. You can even drag it outside of the browser, perfect for when you're working in a different application. And then there's Aria, an integrated AI tool. You can quickly access Aria's command line with the keyboard shortcut Command or Control+/ to get answers to your questions without interrupting your work. Aria can also generate images from scratch in seconds using a simple prompt. Great for when you need a little inspiration. It also works the other way around, so if you upload an image, you can get more information about it thanks to image recognition. And to top it all off, Opera looks great, with multiple themes to choose from, including this one called Midsummer, with mesmerizing visual effects, calming ambient music, and tactile input sounds. Opera One R2 is available now, completely free, so download it using the link in the description. After looking around at several of the options for screens, I decided to keep it simple and use one of the ones made by LattePanda's parent company, DF Robot, since I know it'll work with the Mu. I chose this 11.6-inch 1920 by 1080 touchscreen. With that familiar 16:9 aspect ratio, it's going to be great for most uses. Best of all, this connects straight to the Mu via these two cables, so I won't need to sacrifice any of my USB ports. I have to say I'm pretty impressed with this. It has good colors, contrast, and the touch function works great. For storage, I'll be using a 1TB SSD. This is one of those shorter ones. I'm not sure what the exact term for it is, but I need to stick with this in order to keep things nice and compact. The Mu doesn't have onboard Wi-Fi capabilities, so I'll be using this little card, which fits into the other M.2 slot. It needs antennas in order to function, so I bought these. We also need a speaker. I'll be using this one, rated at 4 ohms, 5 watts. It sounds pretty good for its size, actually. Next, we need a keyboard. When I built my last Cyberdeck, I had never designed a single PCB before, but now that I've got some experience under my belt, I'm just going to design my own custom keyboard. I also caught some heat in the comments for using one of these Apple keyboards, which people didn't seem to be a huge fan of, although I thought it was not terrible. Cool! Why use a magic keyboard though, sad face? Yuck! Apple keyboard? Are you crazy? All that effort and gorgeous design only to have it ruined by the use of an Apple keyboard. Decent keyboard? MacBook keyboard with a Windows device? Are you kidding me? You lost me at the Apple keyboard. Thinks Apple makes decent keyboards? Not gonna make it, bro. Apple Magic Keyboard on a Windows-powered device is cursed. Okay, the people have spoken. No more Apple keyboards. For my design, I decided to go with an orthogonal layout, which might be a little bit controversial, but the ortho layout is actually the more logical design if you really think about it. We're all just stuck in the habit of using staggered keyboards because it's a carryover from the days of typewriters, but honestly one of the main reasons I went with the ortho layout is just that it's more compact. I'm sure I'll get some comments about that though. I also split the keyboard in half because I wanted to add a trackpad in the middle. More on that in a minute. For the key switches, I went with these Kale Chalk Reds. I used these previously in my 3D printed mouse project, and I liked how they felt. But more importantly, they're very low profile and they can be spaced pretty tightly. This will be a very compact device, so I won't have a lot of space if I want to fit a full keyboard in there. Well, okay, not that full of a keyboard. So I created this layout. 5 rows, 14 columns, with the dual space bars taking up 2 key spaces each, and these 2 blank keys at the bottom functioning as left and right mouse buttons. I also mentioned a trackpad. For that, I'll be using this, an Azotec TPS-43. It's really small compared to the trackpads on most laptops, but it gets the job done. This thing communicates with the microcontroller via I2C, a very common communication protocol. Normally, I'd just use an Arduino Pro Micro, like I've done in 2 previous projects. But the problem is that it doesn't have enough pins. See, in order to read the correct key presses, you need to use a keyboard matrix. You need 1 pin for each row and 1 pin for each column, so 14 plus 5, that's 19 pins. But then we also need a trackpad which requires 2 more. So I'm going to go with a Raspberry Pi Pico. They're a little bit larger than a Pro Micro, but they have way more GPIO pins, and they're very cheap and well supported. So, time to design the PCB. To speed up the process, I used Joe Scotto's KeyCAD library. Be sure to check out his channel because he has some really awesome designs on there. I won't go through the whole design process here, but essentially the main thing is to ensure correct spacing. These Kale Chalk switches are meant to be placed on an 18 by 17 grid. I ran the traces connecting the columns vertically and the rows horizontally, and then linked those up with the Pi Pico. Each switch needs a diode. I've used some small surface mount ones and placed them on the bottom of the board to save some space. Lastly, I added 4 connections for the trackpad. Ground, 3.3 volts, SCL, and SDA. And with that, it was time to send the files off to be manufactured. And here they are. I had those surface mount diodes installed by the PCB production company because I hate soldering tiny stuff like this. But I still had to solder on the switches and the microcontroller. That's a pretty easy job though. For the keycaps, I chose these, made by ChosFox. Some people like to go with the all-blank look on custom keyboards, but I'm not that confident in my typing abilities, so I'll keep my printed keycaps, thank you very much. In order to get this thing to actually function as a keyboard, I had to flash something called QMK firmware onto the Pi Pico. Alright, that right there is a functional keyboard, minus the case, which I'll be 3D printing later. Now, I'm going to need some way to power this thing besides just plugging it into a wall, and that means some sort of battery. For my last Cyberdeck build, I just went with the official framework battery since it was made specifically to go with that system, but here there's no ready-made solution. The Mu can handle an input range of about 10 to 20 volts, so a battery with a nominal output of 12 volts would be the obvious choice. Originally I was going to build my own bank out of 18650 cells, possibly even integrated into the main PCB, but here's the thing, this project is already getting really complex, and I've never designed a battery bank before, so there's a lot of things that I need to do more research into. So in this case, I think I'm just going to use something off the shelf. So I decided to just buy a battery bank that would fit my needs and modify it a little bit. I found this one that consists of 6 cells, 3 sets of 2 parallel units in series, giving it an output of roughly 12 volts, perfect for my application. After taking it apart, you can see the 6 individual cells shrink wrapped together and connected to a small PCB with a DC barrel jack, USB charging port, and a big on-off switch. We'll need to modify this slightly, but I'll come back to that later. Okay, now for the hard part. I need to create a custom carrier board for the LattePanda Mu. Now, this part of the project is honestly complex enough that it deserves its own video, so I will be making one. But in the meantime, here's a quick rundown. DF Robot provides an open source KiCad project with all the files needed to create what they call their light carrier, link in the description. So I used that as a starting point. But the light carrier board is slightly too big and the USB and HDMI ports are in the wrong places for what I need. It's also got a lot of stuff that I won't be using in this project, so those parts can be removed. First, I went through the schematic and trimmed out everything that I don't need, like PCI Express and Ethernet. I also added a couple of extra USB connections, one of which will be used for the keyboard, and an audio processing chip to the design, the Max 98357, since the reference file had no way to output sound besides sending it over HDMI. This communicates with the Mu via a protocol called I2S, or at least it was supposed to. Then I had to completely redesign the PCB with everything in the right place. It was quite a challenge for someone like me with no formal education in any of this, but I think I did an okay job and finally got everything connected the right way, or at least I hoped. I sent the files off to be manufactured and assembled, but my order got rejected. Turns out I'd specified the wrong part for the M.2 mounting standoff posts, and luckily they caught it. So I resubmitted it with what I thought was the right one, and it got rejected again. Why? Well, it turns out that one of the reference file dimensions was actually off, and so I had to fix that. Moral of the story, just because you found some file on the internet doesn't mean it's completely accurate. Big surprise there, eh? But would the boards actually work? While I was waiting for those parts to come in, I was hard at work on the physical design of the device. Obviously, I had really started this step a lot earlier because I had to be aware of the general size and configuration in order to design the circuit board at all, but now I needed to finalize everything. The dimensions of the Mu itself played a big part. The Mu is really thin, but it requires cooling. At one point, I considered making the entire bottom of the Cyberdeck be a big sheet of aluminum to basically act as passive cooling, but I wasn't sure how well that would work, so I opted to just use the official active cooling fan and embrace extra thick electronics. I decided to have the screen angled slightly forward so that the thing can still be used while sitting flat on a desk. This also works really well because the thickest part will be at the rear where the Mu and the heatsink stick out the furthest. The enclosure will be made up of a central body shell that will hold all of the parts in the correct place, which will be 3D printed, and 2 metal sidewalls that will give it a lot of durability, plus a lightweight front plate that'll hold the screen in place. To save on costs and allow me to prototype everything, I opted to 3D print the main body structure. Unfortunately, my 3D printer isn't big enough to fit the entire body inside, so I had to divide it in half. These 2 parts will need to be glued together. For the top and sides, I want something a little bit more premium looking and also stronger than PLA. I chose to go with anodized aluminum in this cool dark green color. These parts could be made out of some other material, of course. The left side has cutouts for the battery jack, USB charging port, and the on-off switch. And I also added this carry handle, which I think is pretty cool. The right side has openings for the 4 USB ports and the power button. Both of these also have horizontal rails on the inside edges to keep the keyboard in place and allow it to slide in and out. I also created these 2 arms that attach to each side and can swing downward to form a stand for the device so that it's easier to use at a desk. They serve another purpose as well, locking the keyboard's position in place when closed. And speaking of the keyboard, I designed a 3-part interlocking frame that surrounds it and provides support from the bottom. 4 screws lock it all into place from underneath. There's a little cutout area in the center that the trackpad snaps into, and of course a hole at the back for the cable. This was something that I made specifically for this project. USB micro at one end and a 4-pin JST connector at the other, where it plugs into the main board. This takes up a lot less space compared to a traditional USB port. Now, I was absolutely dying to know if those carrier boards that I had ordered would actually work, since they were by far the most complex PCBs that I'd designed so far. So when they arrived, I tore into the package like a kid on Christmas morning. It's the moment of truth. I'm gonna press the power button. Okay, fan spinning, that's good. Oh, we got something here. Okay, it's loading. Oh, that looks like the Windows screen. Somehow I had actually managed to get everything right on the first try, which, believe me, is not a common occurrence. Except there was no audio. At first I thought, okay, maybe something just needs to be enabled in BIOS, or in the Windows Device Manager, or maybe it'll work in Linux if I install the right drivers. But no, that would be way too easy. It had been my understanding that the Mu supported audio output over the I2S protocol. Why? Well, it says so here. Oh, and it also says so here in the schematic file. So you can probably forgive me for jumping to that conclusion, but it doesn't. Well, not yet anyway. I emailed support and was told that they were working on it, so maybe this feature will be available soon. Who knows? So the result of that was that I was left with no functioning audio, and I had to figure out some way to get the sound from the Mu itself into the speaker. I didn't want to spend the time and money to redesign the PCBs, but after doing some research, I found a simple solution. This little gadget takes audio via USB, decodes it, and amplifies it. All you have to do is plug in a speaker. The only issue was that it was set up to plug into a standard USB port. I wanted it inside of the device, so I started by popping the outer plastic shell off, revealing this little PCB. I then desoldered the USB plug and soldered on some wires that can connect to one of the internal 4-pin connector sockets that I had added to my carrier board. The speaker just plugs into the other end, and the best part is this works out of the box with no extra setup required. So I kind of dodged a bullet here. Now that I have some experience designing PCBs, I'm really trying to get away from these janky, hacked together solutions, but sometimes you gotta do what you gotta do. Before I could put everything together, I needed to do one last little mod. The battery bank's PCB had these big capacitors sticking out really far, which got in the way of the side plates. So I desoldered them and replaced them with equivalent value ones, bent 90 degrees and facing the other way. And of course I had to make sure I didn't mess up the polarity. That would be bad. Additionally, I soldered some pretty beefy wires from the back of the barrel jack so that I could actually power the device. Kind of an important step, really. It took me a bunch of iterations to get all of the printed parts to fit together just right. For the prototypes, I just used some plain white PLA, a whole spool of it, actually. But for the final rendition, I went with this so-called PLA metal filament, which has no actual metal in it, but it looks nice anyway. Those I glued together with JB Weld 2-part epoxy. Super glue is probably fine to use here, but because it sets so fast, it's hard to make sure everything is aligned. So I went with this, and used a couple clamps to hold everything in place while it was drying. With that done, it was time to assemble everything. First, the 2 cables that go onto the screen have to be plugged into the Mu itself. The battery wires also need to get screwed into this terminal on the main PCB. The carrier board slides in on the right side of the device. This is a really tight fit and actually requires the 3D printed body to flex a little bit. Next, the battery bank's PCB slides into this recessed area on the left side. The main part sits here, secured with double-sided tape in order to keep it from rattling around. I also tucked that little USB speaker adapter board in here as well. Alright, now I can put the metal side plates on. These screw into some heat set inserts, which go into the 3D printed part. Now the screen goes in like this. And to keep that in place, the front plate screws into the top. And last but not least, the stand gets bolted on. I used a carbon fiber rod to connect the 2 sides, which are 3D printed at 100% infill for strength. And that's it. Not quite as easy as a Lego set, but not too bad. Now that I'm finally done building it, let's take a look at the features. The cool thing about this device is that there are a bunch of different ways that you can use it. You can have it closed up and use it like a tablet with just the touchscreen. But you can also lay it flat on a desk and slide the keyboard out, which lets you type properly, as well as use the trackpad. If you really plan on using it for an extended period of time though, it can be propped up using the stand with the keyboard out for a more natural viewing angle. Or you can even prop it up with the keyboard retracted to just watch some videos. I'd recommend checking out some of the ones on my channel. An interesting aspect of this device is the fact that it's powered by a 12-volt battery bank. That means you can technically treat it just like a giant phone charger. This USB port on the side isn't connected to the Mu, but you can plug your phone in and charge it faster than a normal USB port would allow. And this barrel jack also outputs 12 volts, so you can use it to power other things as well. The touchscreen is pretty awesome. It lets you use this thing without having to slide out the keyboard or connect a mouse if you don't want to. And the screen works with the software brightness control in Windows, so you can easily adjust that, and it does get pretty bright. Since I did include that HDMI port on the PCB, it's got the ability to output video to an external monitor, which is something that every portable device should have in my opinion. And of course, we've got the 4 full-size USB ports. Not bad for its size. Okay, that's pretty neat and all, but what about the device's performance? Since the Mu came with Windows 11 preloaded onto the onboard storage, I can install pretty much anything I want on this. But I've also set it up to dual boot into Linux Mint, which I installed onto the 1TB SSD. For basic tasks such as web browsing, watching videos, and of course programming, it's great. And that's what I built it for. In terms of specs, this comes in somewhere between a Raspberry Pi 5 and a fully fledged laptop. I'm using the N100 CPU with 16 gig of RAM, as I feel like that's a sweet spot in terms of performance versus price, but obviously any of the Mu models would work. I installed Fusion 360 to test how it would handle a more demanding application, and surprisingly, it did pretty well. It's not quite as smooth as it is on my desktop PC, obviously, but it's really not that bad, especially if you disable anti-aliasing. That really seems to speed things up. I think it's because the graphics capability is really the weak point of this system. Now, this really wasn't designed with gaming in mind. After all, I did axe the PCI Express slot, but there was at least one thing I had to try. I installed Doom 2016, which is an absolute classic, just to see if it could run it at all. Now, as you can see, I'm only getting about 30 to 40 FPS, which is not impressive, and that's with everything turned down to the lowest possible settings. Now, let's address the elephant in the room. This thing is thick, and it's not exactly lightweight either. Of course, those thick metal sides aren't helping, but I don't care because I think they're cool. Personally, I don't mind the thickness. I feel like companies nowadays only care about making their devices as thin and light as possible, and they're more than happy to cut features in order to accomplish that. But if you call this thing a brick, well, you're not wrong. Now, besides the audio workaround I had to implement earlier, there was one glaring mistake I feel obligated to mention. I somehow completely forgot to include battery monitoring. In other words, there's no way to tell how much charge is left by looking at the screen. There's several ways that I could have accomplished this, but the simplest would have been to just include some sort of voltage measurement circuit on the main PCB. Oops. So I threw this thing together afterwards that can plug into the charging port and at least tell me how much voltage is going into the device. If it falls below about 9.5 volts, I know that I'm about to run out of power. Overall, I'm really happy with this build. I mean, just look at it. But obviously there's room for improvement. Anyway, comment below and let me know what you think. Thanks for watching.